Hello class, I hope you're doing great. And this short video is just for you to see the solutions of each of these 10 problems from the final exam. You're gonna notice that it's an extremely simple exam, and I'm gonna demonstrate that. Okay, so let's see, guys. Problem number one: demonstrate that this expression is equal to 1 over x squared. So let's get started. Remember, the way you have to start a demonstration is by actually writing down the same thing as you were given. So you needed to write all of this. And all of this is raised to the minus 1. And that's going to be equal to itself. I know this is a little tedious, but that's the way it has to be done, guys. I made a mistake in here. This is why. There you go. And when you work in a demonstration, guys, you need to work from top to bottom, and if you run out of space, then you go to the other column. But what a lot of people missed, or what a lot of people didn't do, was a separation to separate this column from this column, and that makes things a little difficult to read. If you're going to work in this way from top to bottom, and then when you run out of space, you're going to continue here, please write some division so that your reader understands what you're doing. If you don't write this division, your reader may understand that you're working from left to right and then in zigzag, sort of like this. So that's very important, guys. Okay, so let's do it. What am I going to do first? Well, I'm going to apply the rules of exponents in here. Y to the square over y to the 5. That's going to be y to the cube on the denominator, right? It's going to look like this. And then I'm going to, at the same time, I'm going to apply this rule. I'm going to transform this fraction into this. Because remember that y to the minus 1 can be written on top of the fraction as long as you change the sign of the exponent. So that's the first thing I'm going to do. You need to proceed little by little, guys. A lot of you did very quite long jumps or strides, and that's not a very good idea. Okay, and then y to the 4 over y, you get y to the 3 on top over x, all of this to the minus 1. I ran out of space in here, so I try to tell my reader, okay, I'm gonna continue in this other side. You see what I mean? Dot 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 equals. Okay, let's multiply these two fractions. You're gonna get x to the cube, y to the cube over y to the cube times x, and all of this is raised to the minus 1. We haven't yet done anything to this minus 1. Dot 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 equals. Same thing again, we apply rules of exponents. We cancel y to the cube with y to the cube, and x to the cube over x, that's going to be equal to x to the square over minus 1 dot 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 equals. And as we know, when we have something raised to the minus 1, that's equal to 1 over that something. And that concludes the whole demonstration, right? Finally, we can just wrap it up and write, okay, therefore, what we were trying to demonstrate, which is that this expression is equal to 1 over x squared. That's it. So that concludes the whole demonstration. This is a 5. That concludes the whole demonstration. By the way, I should tell you this, guys. If you didn't do the process in this way, that doesn't mean it's bad. There are several ways to demonstrate a theorem. or to solve a mathematical problem. But the more it looks like this, the better it is, in my opinion, okay? But again, I'm gonna repeat that, guys. You may have done something different, and I may have graded it correctly. Okay, so don't worry about that. It's perfectly fine. Most people did not do this much, by the way. Okay, so that's the first problem. Let's continue to the second one. Well, let me do this instead. Number 2, calculate the logarithm base x plus y of this expression. So what am I going to do? I'm going to do the following. I'm going to write logarithm base x plus y of this expression and since I want to calculate this, I may as well give it a name. The logarithm base x plus y of this, I'm going to call it c. A lot of people did the following. A lot of people wrote, instead of another variable, they wrote x. Okay, they wrote something like this in order to represent like some variable. But this is wrong, guys. You cannot do this. But this is a wrong x. Okay, this doesn't mean the same as this. This is wrong. Why? Because the variable x is already being used in here. So you need to make a difference between your value, which I'm calling c, okay, and every other single value in here. You cannot write x. Although I did not use any points if you did that. Okay, now that I have written this, guys, I'm gonna go to the equivalent exponential notation of this statement, right? What is equivalent notation? It's this. All of this means exactly the same as this. X plus y to the c equals this large expression, right? Many of you did this. That was perfectly good. Okay, and then now that I have done this, how can I find c? Well, just basically by trial and error, just by realizing the following. This expression on the right, this expression in here is basically x plus y to the cube, guys. This is one of them. I mean, this was very simple to see. Why? Because you have already worked with binomials to the cube, both in the previous semester and a little bit in this one. So you should have known that. That was a very simple thing to see immediately. And therefore, you can quite clearly see that if x plus y to the c is equal to x plus y to the 3, then obviously c must be equals to 3. And that's it. I'm done. My conclusion. Many of you did not do this. You need to conclude, guys. You need to conclude your problems. Conclusion: the logarithm base x plus y of this expression, I'm not gonna write it down, is equal to 3. This is the most perfect answer that you can come up with. Don't just leave like a lot of people just wrote the 3 like isolated, and they expected me to understand that was the answer. This is incorrect. Even though I can understand that, it's technically incorrect. You should always conclude your problems in the right way. If I'm asking you for the calculation of this expression, then you should tell me, teacher, the logarithm base x plus y of this expression is equal to 3. That's the most neat way to do it. Let me make a pause, and I'm gonna come back in a minute. Okay, next problem number 3. Calculate this expression if possible. Like, we need to add all of these terms, and we have to raise it to the addition of all of these terms if possible. So let's see. These are, as seen, these are infinite series, right? And all you have to do, guys, is okay, let me talk about the first series first. which is this one. Three plus one third plus etc. Okay, so can we add this series? Yes, yes we can. Why? Because it has the following characteristics. Its first term is 3, and the ratio is one third. And remember that when you have an infinite sequence whose ratio is one third, I'm sorry, whose ratio is between -1 and 1, then you can get the sum of the infinite terms. Okay, and that sum is going to be simply the first term over 1 minus r. So basically, the sum of all these terms is going to be 3 over 1 minus 1 third, and therefore this is going to be equal to 3 over 2 thirds. Let's continue here. Can you see how I'm working? I work from top to bottom, and then I make the division, and I work from top to bottom, make the division, etc. You need to make things easy for your reader, guys. And it's not because it's me, but that's the way it has to be done. Okay, and therefore this is equal to 9 over 2. So that is the series for the first. That is the first series. That is the first series. Okay, and then the second series is pretty much the same. Right? Pretty much the same idea. The first term is 1. The ratio is 1/2, and therefore we can calculate the sum of all the terms as 1 over 1 minus 1/2. This is going to be equal to 1 over 1/2, and this is going to be equal to 2. Okay, therefore, notice how I use words. Therefore, 3 plus 1 third plus blah 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 raised to the 1 plus 1/2 plus blah 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 is equal to 9 over 2, because that's this much, and raised to the 2, which is this much. And that's it. You can just leave the answer right there, guys. Conclusion. Well, that's actually a conclusion. That is a perfect conclusion. It's a good idea to box it. And that's it. That's it. Problem solved. Not difficult at all. A lot of you, I don't know, 20-30% just try to do this very quickly. You don't explain many things. You just go directly to like something like this, and it's not the best, guys. Try to explain more. Try to be more thorough. Okay, next, number 4, simplest problem of all. Calculate all of this expression raised to all of this expression. All I need to do, guys, all I need to do is this. Sorry. It's problem number 4. It's not possible because the series 1 plus 2 plus 4 plus etc. diverges because its ratio is equal to 2. Okay, and if you wanted to really make it like really good, and a series only converges for ratios which are greater than -1 and less than 1. That's it, guys. You see, it took me 1 minute to solve this problem. This is a perfectly valid reasoning. That's it. You did not even have to calculate this thing. You didn't have to. As long as you gave me something like this, that was the correct answer. So you can start to see how simple the exam was. Suppose you're given an infinite geometric sequence whose first term is u1 and its ratio r has the characteristic that r is greater than -1 and less than 1. Explain why the sum of all the terms in this sequence, represented by the symbol, can be written as this formula. Okay, many of you in this problem number 5, many of you, I think about 20% or something, you just repeated what I said what I said in the problem. You basically repeat it in some ways, what I said in here, and that's not a demonstration, guys. That's not an explanation. What you have to do is this. Number 5. We know that the sum of the first n terms of a geometric sequence is given by the following formula. It's u1 times 1 minus r to the n over 1 minus r. Okay, so we know this formula, and this formula is in your formula booklet, right? Okay, period. Now, if we want to add all the terms of an infinite, I'm sorry about my writing, of an infinite geometric sequence, then n approaches infinity, right? Because that's what we're doing. We are basically summing a lot of terms, and that means that n, I'm not gonna say that n equals infinity. N approaches infinity. That's the best way to say it. Okay, period. Therefore, we have s sub infinite equals u1 times 1 minus r to the infinite. Remember, this is abusing the notation, but that's the way I told you, so it's okay. And this is equal to u1 times 1 minus 0 over 1 minus r. Why? Because when we raise, I'm gonna run out of space. When we raise a number between minus 1 and 1 to a large exponent, then the result is practically 0, and that's it. That's it, right? So when I raise, since I'm giving you as a premise that r is between minus 1 and 1, then when I raise that tiny number between minus 1 and 1 to the infinity, or to a very large exponent, remember, this is abusing the notation. Be aware of that, guys. Then this is going to be pretty much 0, okay? But you need to explain why. I mean, many of you just went like, they wrote r to the infinity, and they were like, okay, this is 0, but you did not explain anything. Okay, and then once I have done this, basically this formula becomes, once you take away the, I mean, 1 minus 0 is 1, and u1 times 1 is u1, so that's it, right? That's the same formula. So you see, you need to explain, guys. You need to write words. Don't just assume that when you just write formulas and formulas and formulas and numbers, many times I have no idea what you're thinking. If you don't explain anything to me in the same way that I'm telling you right now, I cannot know. I need to interpret what you're saying, and that's not okay, guys. That's not okay. You need to learn that mathematics is not just about formulas and symbols. You need to express yourself in words. You need to make your reader understand you. You need to learn that as quickly as possible. Let me make a pause. Okay, next problem, number 6. Demonstrate that for any natural number n, we have that the product n times n plus 1 times n plus 2 can always be perfectly divided by 2. In other words, the division will yield a natural number. Same thing, guys. By the way, you must realize that number 5 and number 6 and something very similar to number 7, they were in the workbooks. They were in the workbooks. So let's see. So basically, I want to demonstrate that this expression is divisible by 2. Demonstrate that this expression over 2 will give me a natural number, or in other words, that the division of this over 2 will be an exact number, an exact natural numbers. This is divisible by 2. Okay, how can I say that? How can I demonstrate that? Demonstration, very simple. Demonstration. A number is divisible by 2 if that number is even. And we talked about this in the workbooks and in the class. Okay, so as long as I can demonstrate that this expression is even, and even this times this times this, all of this is an even number, then I'm done. Okay, and then we talked about some criteria to find when a number was even. Okay, for example, we talked about this. When we have an even number times an even number, we get an even number. When we multiply an even number times an odd, we get an even number. And when we multiply odd times odd, we get an odd number. We talked about this in class and in the workbooks. Okay, so basically, we must realize that as long as you multiply by an even number, then the result of the multiplication will be even. You see? So now, let's suppose this. Suppose n is even. Suppose n is even. Then the proof is completed, right? The proof is completed because n times n plus 1 times n plus 2 will be even. Why? Because n is even by assumption. You see? And when I multiply this times this even number, the result will be even. And if this number is even, then it will be perfectly divisible by 2. That's it. But that's just the first part. Now, suppose the other alternative. Suppose n is odd. Okay. Then n plus 1 is even, right? I mean, we always get this odd, even, odd, even, odd, even, etc. Okay, that's very easy to see. Okay, so n plus 1 is even, and therefore n times n plus 1 times n plus 2 will be an even number. Why? Because this number is even, and as long as we multiply any number by an even number, we will get an even number as a result. And that's it. Proof completed. With this argument, you could have demonstrated this thing. Very simple thing, guys. Next, demonstrate that for any numbers x and y such that x is greater than 0 or x is positive and y is less than 0 or y is negative, the expression x to the cube minus y to the cube minus 3x squared y plus 3xy squared is always positive. Okay, now you should have noticed, guys, you should have noticed that this looks very similar to this, right? It's pretty much the same. You should have realized that expression can be factorized as a binomial to the cube. So, basically, problem number 7. Okay, we have that x to the cube minus y to the cube minus 3x squared y plus 3xy squared is equal to x minus y to the cube. Again, a very simple thing that you should have known by now. Okay, so if this is equal to this, and if I'm told that x is always positive and y is always negative, then x minus y is always positive. Positive. Why? Well, because x is positive, and because since y is always negative, and I'm multiplying a negative number times minus, all of this will be a positive number. So positive and minus y is positive. Okay, and then when you raise a positive plus positive to the cube, then it remains positive, right? So that's it. You see, that's it, guys. I mean, all that I just said, like all the stuff that I just said with my mouth, if you wrote it down, then that makes a perfect argument. Okay, and that's it. I don't want to write it down. I don't want to take too much time into doing this, but that's basically the whole idea. Now there were other ways to demonstrate that thing. Some other people, what they did was, and they were more like they did the following. They were more they worked little by little. Like they did not write this as a binomial to the cube. That's fine, no problem. But they went like this. Okay, so they were, look at this number, x to the cube, and then they wrote, since x is greater than 0, then x to the cube is greater than 0, right? When we raise a positive number to the cube, we always get we also get a positive number. And okay, fine. And then let's look at this, right? Okay, so we have minus y to the cube, and y to the cube, since y is negative, y to the cube is also negative. And when we multiply by minus, we get that this is a positive number. Okay, and they did something like this by paying attention to every single one of these terms, and that also works. That also works if you did it correctly. Okay, so that is problem 7 for you. Okay, problem number 8. We have a worm that crawls a certain distance every day. The first day it crawls 105 centimeters, and every next day it crawls 1/4 of the distance that it crawled the previous day. Will the worm ever reach a point which is 142 centimeters away from its starting place? Ignore the length of the worm itself. Consider it as a mathematical point. Okay, so basically, what do we have here? We have the worm. I mean, you can consider this as the real line, right? The x-axis, and the worm is here at position 0 in the very first day. And then in the very first day, he walks, crawls 105 centimeters, right? And then in this is the first day, by the way, first day. And then in the second day, it's gonna travel 1/4 of the previous distance traveled, which was this. So this is from here to here. Well, I should do this instead. I should do this. This is 105 centimeters. And then this, all of this is 105 times 1/4 centimeters. You see? And then in the third day, he's going to cover 1/4 of the previous distance covered, which was this. You see? So it's 105 times 1/4 times 1/4, and so on for the rest of the days. Okay, so we can see that it's an infinite geometric sequence. The first term is 105, and the ratio is 1/4, right? So that is the sequence. Now, what we want to find out is whether when we add all of the distances crawled in every day, whether the worm can surpass this distance of 142 centimeters. So let's see. Let's get the sum of the infinite terms of this geometric sequence. This is the formula, and then we're gonna have 105 over 1 minus 1/4, and when you calculate this, you will get 140 centimeters. So this is the, let's say, the limit to which the worm can aspire if the worm keep crawling for all eternity, but it's never gonna go beyond this. Therefore the worm will not reach 142 centimeters because its limit is 140 centimeters. Okay, that's it, guys. I repeat, pardon for my handwriting because I'm doing this very quickly, but you get the idea, right? Okay. From number 9, demonstrate that this expression is equal to 1 over m. We did something similar in a workbook. So 1 over m minus 1 minus m over m to the 4 over m minus m to the square is equal to itself. I'm going to start the demonstration in this way by applying the law of identity that says that everything is equal to itself. Okay, then dot 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 equals, let's see, I'm going to keep this untouched for the moment, minus m over m to the 4 over m, that's going to be m to the 3 minus m squared. Then dot 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 equals 1 over m minus 1 minus m over, I'm going to take an m squared in here as a common factor, and I'm going to factorize in this way. Okay, I make a division to explain my reader that I'm going to continue over here. Then dot 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 equals 1 over m minus 1 minus, by applying the laws of exponents, m over m squared times this. I can reduce these two things, right? I can come up with this. Okay, then dot 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 equals, now in order to make this fraction with the same denominator as this one, all I need to do is multiply up and below by m. I can do this, guys. M over m times m minus 1. You see? Why did I do that? So that now I can have two fractions with equal denominators and I can subtract them easily. Then dot 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 equals, this is going to be equal to m minus 1 over the common denominator that they have. And then finally dot 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 equals, I take another color, I cancel these equal factors, and I'm done. What is dot dot dot? Dot 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 is all of this, right? Which is kept the same throughout the demonstration. We close with the tombstone halmos. This is not necessary, but try to do it. And that's it, guys. Demonstration completed. Okay, and finally, this one, explaining some of these concepts. I believe 99% of you got this correct, so I'm not gonna go in there. So that's it, guys. You must realize that the exam, I mean, we saw all of these things, guys. Basically, you cannot really say that we didn't. So I'm gonna stop the video right here, guys, and thank you so much.